All right, so welcome to the February meeting of the Delaware Astronomical Society. First, I'd like to welcome any new members. Would anyone like to introduce themselves who are new to astronomy or to our club? Any new members?
I would say there's several people here from Chester County.
Oh, yeah, absolutely. Introduce yourself.
That's me. I'm the treasurer of that club. And I see Chuck Atmore is here. And who else?
Yeah, hi, it's Ed Damero. I'm here. I'm sorry.
Chuck is here. David Toth is here. Who else? Ed Damero is here. So yeah, we have a good representation from Chester County tonight. That's great.
Great. Yeah, I'm glad this is continuing to work out. I don't know if others, but I sat in on your meeting last week. Actually, until I lost power. my electricity went off about 45 minutes into the talk.
You did a great job, didn't you?
Yeah.
That's awesome. I think it's really cool that we can get collaboration like this with the other clubs. At least we can get something good out of this pandemic.
Yeah.
Really nice.
I was about to say that. That's very good. Yeah.
I'm going to be sending you an email tomorrow probably about beginner astronomy classes. Our club is gonna, as normal, offers those through the Chester County Night School, but they are on hiatus right now because of the pandemic. And normally we would ask our members who want to take those classes to go through them because it's a good, support they do have a good mission, but we're going to offer them for free. We're going to open it up to DAS, CIS, and DVAA and our own club's new members for beginner astronomy classes.
Yes.
So I'll get that to you in a day.
Fantastic.
I appreciate it. Sounds good.
All on Zoom, of course.
Yes.
I'll be coming to you in a day or two, okay?
Cool.
Very nice. Also, there is an AP SIG meeting coming up on Saturday at 1 p.m. Did you want to mention something about that, Bill, real quick?
Yeah, we don't have a special topic yet, but I'm looking at deep sky imaging cameras as the likely special topic. So hope to see you there if you're interested.
Very nice. And let's see, Jeff, did you want to announce the binoculars real quick?
Yeah, so the DAS has just recently received the donation of some really, really nice binoculars from Mount Cuba. And I'll share my screen real quick. You guys seeing this?
Mm-hmm.
Yep, we got donated 3 pairs of really nice binoculars. The first pair are some Fujinon 16 by 70s. The second pair, oops, come on, are Vortex Razor HD 12 by 50s. Both of those, again, those are specific models. I looked them up. Very, very excellent binoculars. The third ones couldn't quite get as much details. These were photos sent to me by Kim Green, who is the Mount Cuba administrative assistant. So these are Nikon 10 by 70. So all 3 of these have been donated to the DAS by Mount Cuba and are currently residing on the shelves of Mount Cuba's storage area. Of the DAS storage area. So again, hopefully once we start getting back to normal, we'll be able to take good advantage of some really nice binoculars. So big thanks to Mount Cuba there.
Fantastic.
Very cool.
We really appreciate that. We thank Mount Cuba deep from our hearts. It's wonderful that they've done this for us. I think it'll really help our programs when we have classes and things like that to let people look through binoculars and get that experience. And then they can compare it to telescopes. So that's really cool.
Yes, I have a pair of Fujinon 16 by 70s. I like them an awful lot. They're very nice.
Yep, very good. All right, Bob, talk with the dues.
Yeah, I just wanted to thank everyone who's renewed their dues. We have 106 members that have renewed their dues so far this year. I did send out a notice today. If you got a note from me, then I haven't gotten your dues yet. So if you could send in your dues before the end of the month. At the end of the month, anyone who hasn't paid their dues no longer are active members of DAS. So I encourage you to get your dues in. But again, thanks for everyone who's gotten their dues in.
Very good. And just to let everybody know, the DAS does now have a Zoom account, like a professional Zoom account, and we're using it right now. We've used it for a number of meetings over the last month, and there's been no hiccups with that. It's worked quite well. And we did an experiment this month where we went into a breakout room to have our board meeting. Didn't seem to cause any troubles, and some people were socializing outside before we came out of the meeting. So it was very good, worked very well. We had no issues, I believe. So that's good. Any other announcements before we get started with our main program? If not, I'll turn it over to you, Jeff.
All righty. So before I announce the speaker, I just want to go over the typical Zoom protocol, just to keep the distraction and the noise down so we can all hear our speaker as clearly as possible. What we will do is Rob is going to actually go ahead and mute everybody.
Yeah, right now.
What I would encourage, in fact, yeah, why don't you go ahead?
Yep.
Right. Then I will unmute myself, the rebel that I am. If questions come up during the talk, first level would encourage people to use the chat window. Rob and I will be monitoring the chat window and, try to find appropriate moments to break into the talk and ask those questions. Or what's happened in the past, sometimes other club members are able to answer the questions within the chat. So that's kind of a neat little interactive aspect. Again, just the idea of to be able to keep the momentum and the flow of the talk, rather than people interrupting and talking over each other, we'll use the chat feature. And then if the speaker's up for it, at the end of the meeting, what we'll do is we'll open up the gates, take off the shackles, and allow people to then directly open up and ask questions and get a little bit more interaction there. So again, just a big reminder, please, try to remain muted. Rob and I will be monitoring the chat window and feeding questions to the speaker as we say. So I don't have to keep saying the speaker. This month, we are honored to be joined by Gaspard Duchene, who comes to us from UC Berkeley, where he is an associate researcher and lecturer. He received a PhD from the University of Grenoble. I'm not even going to try. I'm Grenoble. And he's going to be giving us a very interesting talk. And I remember a bunch of years ago when I was first hearing about the idea that exoplanets, their existence could be inferred from data, was just a really amazing concept to me. The fact that you could look at the blips in the light curve or the wobble and infer the existence of planets, I thought that was super amazing. And then fast forward just a handful of years ago when I heard that we were then directly taking photographs of exoplanets, just completely blew my mind. And so that's a little bit of a segue to lead into Gaspard Duchene, who is going to be talking with us tonight about exoplanets. Gaspard, it is all yours.
All right, thank you, Jeff, for the nice introduction. Let me make sure I share my screen. And the right screen, ideally, would be best. That should do the trick. And let me know if that works, if you can see the whole screen. All right, perfect. Well, thank you. It's a great pleasure to be with you all tonight. It is kind of a little odd for me. It's my first time actually giving a talk to a public audience or an astronomical society through Zoom, although, of course, we've been in Zoom land for the past year or so. In a sense, I'm a little sad because that means we're not together all in the same place and we don't have the chance to directly chat, but I definitely welcome the chance for questions and interaction during the talk or at the end of the talk, as was suggested. On the flip side of it, despite all the bad side about the pandemic, of course, I don't know that without the pandemic, I would be here tonight talking with you, obviously, because I'm just on the other side of the world, and who knows, or the US, and who knows if I would have had a chance to travel through Delaware. So at least I got that. I guess I get to thank Richard for the connection there. So yes, my plan tonight is to tell you a little bit about the methods we're using to try to take images of planets around other stars, and the challenges that come with that, and the discoveries that have been made, or some of the discoveries that have been made in the recent years. So I wanted to start this presentation by staying in the solar system before we talk about planets around other stars. And that's why I like starting with this particular picture here in my background. These are the backlit rings of Saturn taken by the Cassini mission before it was plunged into the planet itself. The reason I like this picture, other than loving Saturn's ring, like I'm sure many in the call tonight, is that there is a little speck. Oh, let me do one more thing. There we go. Nope, not here. there is a little speck here down at the bottom that actually is the Earth. And if I had not circled it in here, and if you'd never seen the picture before, you would have been hard pressed to figure out that this was a planet, let alone the Earth. And we're just at Saturn's here. We're not, light years away as we are when we try to look at planets on other stars. So you can already get an idea of how difficult this exercise is to take pictures of planets around other stars. Now, of course, I'll walk you through what is sort of like the obligatory, why is my not working? I don't know. Sort of slide of telling you about, searching for planets around other stars. As Jeff mentioned, just a quarter century ago, the idea that there were planets around other stars was something that mostly philosophers were discussing. Religious people, scientists for centuries have talked about the possibility of planets around other stars, and but it remained sort of an esoteric discussion. It was felt like it would be impossible to ever have a chance to actually find stars or stars that have planets around them and be convinced they were planets, let alone study their detailed properties. However, that didn't stop our imagination. Of course, for a long, long time, planets around other stars were part of science fiction. And as any good science fiction story, there is something that eventually becomes true. There's a good science to be taken out of that. So without talking about specific stories or science fiction stories, the study of planets around other stars has now become central to modern astronomy. And I was just last month, was it last month? Yeah, last month at the American Astronomical Society meeting. And out of all the plenary and parallel sessions organized, I would say a solid 20% of them at least were centered on exoplanets, planets around other stars. Different kind of sessions, some technical, some scientific, some about imaging, some about other methods, theory, you name it. But it has become one of the largest fields of modern astronomy to look at planets around other stars. So it's no longer science fiction, it really is science. In fact, the breakthrough occurred about 25 years ago, something that came back in the news just last year when two Swiss astronomers were awarded the Nobel Prize for the discovery of the first planet around another star, 51 Peg. And that sort of happened, well, let me get that right. Yeah, that happened just when I was starting to do research. So it sort of like followed me throughout my entire career, this study of planets and the discovery of the first one. And by now, as we'll see in a second, the knowledge that there are many, many, many planets out there. So once it had become a science, we moved on from the question of like, are there planets, or can we convince ourselves that there are planets around other stars, to that of what can we learn about it? And of course, to learn about planets around other stars, it's not just enough to find just one or to be able to study that one in particular. You want to know about planets at large around many stars, try to determine the statistical properties. How common is it to find planets? How different or similar are they to our solar system planets? Are they larger, smaller? What kind of stars host planets more than others? And all these kind of questions are addressed primarily by statistics, not by studying just one planet. Now, this little plot here, which is probably already out of date by a couple of weeks, and I'm sure it's already out of date, that's how fast things go, illustrate the total number of planets that we know around other stars as a function of date. Of course, we're in 2021 on the right-hand side of the diagram here, and you can read off the vertical axis that we know something around 4,000 planets or so. So we do know that a lot of planets by now. As you can see, the field exploded over the past 15, 20 years. We went from just knowing a handful to knowing, again, hundreds to thousands of planets. But the one thing I want to point out in this diagram here is the color coding. And I have to apologize right away in case there are some colorblind astronomers in the group here. Unfortunately, the two biggest bars are red and green. And this color coding has to do with the method by which we find planets. And the red and green stand for the two most prolific methods of identifying planets around other stars, namely the radial velocity method and the transit method. I'll briefly mention what they are in just a second. At the very top of these histograms, of these little bars, you can see a few other colors, other methods of finding planets, one of which is the imaging of planets, which is the focus of tonight's presentation. But briefly, let me just say a few words about these two main methods, the radial velocity and the transit method, because those have been the way we've studied planets for the most part over the past 25 years. So the radial velocity method hinges on the fact that when a planet goes around a star, by virtue of Newton's second law, the star is also a little bit moving. It's moving around the center of mass of the system, And as the planet that you can see, let me do one more thing. I forgot to do, where is that? Sorry, I forgot to find my spotlight. There it is. We have here a little planet that we don't never really see directly. It's going around the star, but as the planet goes around the star goes in this little circle. As it does, there are moments when the planet is actually moving. Oops, sorry. Let me go backwards. When the star, is moving towards you, some moment when the star is moving away from you. And by virtue of the Doppler shift, this makes the light of the star change a little bit. Blue shifted, red shifted, blue shifted, red shifted. And by measuring this blue shift and red shift, we can measure the velocity of the star. And this is how the first planet was discovered, 51 Peg, because that particular star, 51 Peg, happened to go back and forth towards us, away from us, towards us, away from us, with a very regular pattern. That was the evidence that there was a planet tugging onto that star. The second method we often use is the transit method, by which we wait for a planet to just pass in front of its star, like Mercury does in front of the sun in the bottom right figure here. When that planet passes in front of the star, it blocks a little bit of the star, and although we cannot see the nice dark circular shadow of Mercury or the other planet, we can see that the star becomes a little fainter. So if we can measure the fact that the star dips in brightness by something like 1% or less every few days or so, that means there's a planet passing in front of it in a regular pattern. Now, this method has now become the most prominent method of identifying planets, in large part thanks to the Kepler mission that NASA launched, well, almost 10 years ago now. But it's actually feasible to perform this experiment even from the ground, as Richard could attest. I know of some UC Berkeley undergrads who can do that with a 30-inch telescope. Now, it's complicated. It's not as easy. Again, Richard could speak to that. But it is feasible from a relatively small telescope to make that measurement. And that's why also we know so many transit planets. So we have two great methods to find planets around other stars: radial velocity, transit. They provide somewhat complementary information about the size and the mass of the planets. And they're applicable to different kind of stars. There's some subtlety there, but they're very prolific. As I mentioned earlier, we know thousands of planets through these two techniques combined. So why are we bothering trying to take an image, a direct image of a planet right next to a star, if it's difficult, as I will explain over the next few minutes, and if we have methods that work just fine? Well, first of all, I don't think I need to convince an amateur astronomer audience that an image like that on the left is all the more speaking to us than any kind of graph that scientists love to look at, like the ones on the right here. Sure, they contain lots of scientific information and they're extremely powerful, but ultimately getting a nice image like the one on the left here, you can just see the little specks, B, C, D, and E, the 4 planets around this one star, HR 8799, which I'll get back to later on during the presentation. So an image is much better than anything else if we have nothing better. It's just more powerful. But it's more than just getting an image is nice and it captures the audience. We can make a nice press release out of that. It will capture the imagination much better than any of the other 2 plots on the right. There is a lot more we can do if we can image the planets around the stars. First of all, if we wait a little bit, we're going to see these planets move around the star because they all orbit their parent star, just like the planets of the solar system orbit the sun. So we can study the orbits of the planets by just waiting a few years and seeing where they go around the star. That's immediately information about the structure of the planetary system that we're looking at. In addition, if we're able to get a powerful enough instrument to take the light of the planet and then pass it through a spectrograph, an instrument that disperses the light as a function of wavelength, we can study that spectrograph and infer something about the composition of the planet, something we do a lot of times in astronomy with all sorts of objects, not just planets, stars, galaxies, you name it. And if you do that, you might get curves that look like these crazy curves in these 2 plots here. I don't want to go into any details here, except to say that each of these curves are models of what we think the spectrum of a planet might look like. And the only thing that makes differences between these planets, or excuse me, these curves, these model curves, are the physical properties we think those planets might have. Their temperature, their composition, whether they have clouds or no clouds, whether they have hazes of dust or not, and so on and so forth, make all of these spectra look very different. So if we can take a spectrum of the planet and compare it to all these models, we might be able to say a lot about what those planets are made of and their physical condition. And again, this is something that's much harder to do if you do not separate out the light of the planet from the light of the star. So direct imaging is extremely powerful to achieve that. Now, the problem is that the radar velocity method and the transit method are relatively easy to implement. There are some technical instrumental difficulties, which is why it took so long to mature the technology to do it, but it's not too complicated. It's basically normal instruments just pushed to high precision. The imaging of a planet around the star is much more challenging. And to sort of convey that sense, I'll walk you back to just about a couple of months ago, when I'm sure many of you have tested your eyesight with the astronomical sky by just trying to look at the Jupiter and Saturn conjunction. I'm sure that was a big thing in your society at some point in December, right? So I found this nice montage of picture in the center here showing you Saturn and Jupiter getting closer of about, of course, a month or something like that, I believe. And the moon is here to scale to give you a sense of how close Saturn and Jupiter were. And they were relatively easy to separate out. I suspect most of you in the audience who tried to do that were able to see both planets at once. The image on the bottom right, of course, has been zoomed in so we can see the rings of Saturn and so on. But the conjunction was an idea of, gave us an idea of how well we can find something fainter right next to something brighter, Saturn right next to Jupiter. Now, the image on the right has been zoomed in roughly 30 times, if I do my scaling right. And more importantly, the brightness ratio between the two planets was about 10 to 1. Saturn was about 10 times fainter than Jupiter at the time of the conjunction. So if you could see that, that's what you would see. You would be able to see something pretty close in the sky, a fraction of the size of the moon, and a factor of 10 in brightness ratio. Pretty easy. Now, if you want to really challenge yourself with your eyesight, you go at least a step further and you try to see if you can see Jupiter's satellites. The Galilean satellites that are orbiting around Jupiter are supposedly an extreme test of eyesight. There has been claims of being able to see some of these satellites with the naked eye, without any telescope, any binoculars, any nothing, finding just essentially like a string or a cable or something like that to mask out Jupiter in just the right angle. And you might be able to see probably Callisto, which is the furthest away satellite of Jupiter. Now, again, this is much harder than the Saturn-Jupiter conjunction because it's a lot closer in. Again, here the picture of Jupiter with the 4 satellites on the right is zoomed in about 25 times. But it's not just the fact that it's closer in the sky that makes it difficult. It's also that it's a lot fainter. Now, the brightness ratio, the contrast between these satellites and Jupiter itself is about 1,000 to 1. So now you need to see something that's 1,000 times fainter, and it's a lot closer to Jupiter than Saturn was back at the time of the conjunction. Now, I'm not sure I believe any of the claims that the satellites of Jupiter have been sighted with direct eyesight. I've read a few things, and the jury is still out there as to whether it really happened, but it's probably the most extreme thing you might hope to be able to achieve with your naked eye. Let's put it that way. Now, these numbers I threw at you here with this example is to prepare you for the actual numbers we're facing when we're trying to image the planets around other stars. So here is a simulation of what the solar system would look like if we were to look at it from 45 light years away. So some star pretty close in the galaxy, looking up into the sun. The sun in this image is right in the center. It has been blocked by a little mask. I'll talk about it in a few minutes. And we can see the Earth. We barely see Venus. It's right at the edge of the mask. It's not clear whether it's very nice or not. And Jupiter is definitely present there. We can see the Earth and Jupiter at least very clearly. And then the angular scale, I couldn't put the moon in there to scale because it's so big, you wouldn't be able to see anything. So I had to revert back to using the units that astronomers use all the time, arc seconds. And the bar at the bottom here indicates 1/10 of an arc second. Now, you probably don't have 1/10 of an arc second as a scale in your mind. So that helps, I can tell you, it's about 1/20,000th of the moon diameter. So imagine the moon, take 1/20,000th of that. And that's pretty small, so you may not quite get the proper idea of what that means. So the other way to think about it, it's about the size of a penny as seen from 25 miles away. So that might put into context how far away or close from the star do we need to find our little planets. It's about that scale of 1/10 of an arc second. Oh, and what I didn't mention is, it's not just very close to the star, it's also a lot fainter. Now it's 1,000,000,000 to 1 contrast ratio. So we need to be able to see something incredibly faint, really close to something quite bright, that star right in the middle of the image here. So it's a real tough challenge. And that is what astronomers have been struggling to achieve over the past well, pretty much 25 years since planets have been known around other stars. They've just been longer to achieve because it's technically much more challenging. So one sort of simple way of presenting the problem is saying, like, we're trying to find a firefly that's flying right next to the lighthouse. And we're sitting right there, we're staring at the lighthouse, and all we can see is the lighthouse. How can we ever find a firefly? So we need a couple of tricks to achieve that. And the first one is, because we want to see something really close to the star, it's a very fine detail, we need very high resolution, angular resolution. And for astronomers, what that means is we need a very large telescope. Probably all learned and studied a little bit about how larger telescope always give you higher resolution. You can see more detail in any kind of images. And that is what has driven, in large part, the race towards larger and larger telescopes, just like you're doing at Mount Cuba, right? You're going from 24 inches to 50 inches. You're doubling up. In principle, it gives you twice the spatial resolution, the angular resolution. You can see more detail in the objects you're going to look at with that new telescope. So, of course, building a larger telescope is feasible. We now have telescopes on the scale of about 10 meters for the largest professional telescopes on the ground. And those are quite large, therefore can achieve very high resolution. But it's not so simple. And to illustrate this point, I'm going to show you here an image of a globular cluster. And I don't remember which one it is. Maybe some of you in the audience know the name of the cluster. You can recognize it by just looking at it. It's one Messier something that I know, but I don't remember the number. And this is the Hubble image of that particular cluster. And of course, it's millions of stars put together into this familiar shape. Now, I'm going to overlay on top of that an image taken with the Gemini telescope, which is an 8-meter telescope. So it's like 3 times larger than Hubble. It's down in Chile. And here's the image. Okay, and I'm going to flip back and forth. And as I flip back and forth, you can probably see that all the stars line up just fine. It's the same stars we see in the 2 telescopes. But at the end of the day, it's quite clear that the Hubble telescope image is just sharper, it's crisper. You can see more stars, it's finer detail than if I go and look at the Gemini image. And yet, Gemini is much larger. So something doesn't jive up here, there's something wrong. So what's going on? Well, it turns out, if you build a telescope and you take an image of a star is essentially infinitely far away as far as our telescopes are concerned. So it's just a little point of light. And what we get is that that point of light, by the effect of diffraction of the telescope, gets spread out into this circular shape, what we call an airy pattern. And the larger we make our telescope, the smaller that little area becomes and gets sharper and sharper and sharper as I build larger and larger telescopes. But if I keep pushing to larger and larger sizes, something weird happens. The image gets very blurry. And the reason for that is, although, yes, the telescope being larger, I should be able to see more detail, I'm getting into trouble because of the atmosphere that is in between me and the stars we're looking at. And that atmosphere, as we're all familiar by the stars that twinkle all the time, is making this blur in the images. And that blur prevents us from using a large telescope and right away get the sharpest possible image we would like to. Now, not only does the atmosphere makes the images extremely blurry, it also keeps changing pretty much every millisecond. So if you just take a snapshot of what a star looks like through a big telescope, it looks like what you have at the bottom animation here. It's not a real-time animation. It's a bunch of images taken in sequence, but maybe like once every second or so. And you can see that the atmosphere is just changing all the time. So you cannot just say you get a very blurry image. The way the image is blurred is changing all the time. And that is why large telescopes are having trouble into getting very fine detail, because the atmosphere keeps smearing things out, basically. So although we know how to build very large telescopes, this is a major problem if we're trying to find very small details, like a planet right next to a star. We need to beat that down. We need to find a method to fight against this atmosphere. Now, obviously, the ideal way is to get rid of the atmosphere, but apparently the rest of humanity doesn't like that, so we don't do that. We leave the atmosphere where it is, and we find some other way. Now, one pretty easy way, quote unquote, is to go above it. We launch some of our large telescopes up in space, and at some point, hopefully later this year, we'll be launching the James Webb Space Telescope, the next big telescope to go up. Hubble has been out there for something like 30 years now. And those, of course, don't suffer from the presence of the atmosphere because they are just above it altogether. However, it's extremely expensive, and if something breaks down, then we can go back and fix it. Well, we were able to do that for Hubble. We will not be able to do that from James Webb. So we just hope, fingers crossed, that everything goes just fine when they launch and deploy everything. However, because most telescopes are on the ground below the atmosphere, we need a method to try to fight against the atmosphere. And that method, the best method we've designed so far, is called adaptive optics. And the idea of adaptive optics is to try to find a way to sense how the atmosphere is blurring the image. So the best analogy, it's not a perfect analogy, but the best analogy is to look at the surface of a pool like we have here, to look at the light and shadows game being played at the bottom of the pool, and to use that information to infer the shape and the movement of the ripples on the surface of the pool. We know that it's the ripples on the surface that creates the shadows at the bottom. And in principle, we should be able to look at the shape at the bottom and infer what's happening to the ripples. That's what we do with adaptive optics. Once we've inferred what the ripples are, we then use a mirror that we can push and pull on. We call this a deformable mirror, not a formable mirror. Apologies for that little mistake here. It's a deformable mirror. And we push and pull on it to compensate exactly for the ripples that the atmosphere has introduced in the image. And by virtue of doing that, we can send light to our telescope camera that has now been corrected for the effect of the atmosphere. And therefore, we get a much sharper image. Now, of course, remember, the atmosphere changes every millisecond or so we need to do that every millisecond. So every millisecond, an adaptive optics system senses the blur that the atmosphere has introduced, determines what it needs to do to compensate for it, and applies that correction in a closed loop system. And that's how large telescopes are now able to achieve similar to or even higher resolution than Hubble Space Telescope, because they actually are larger, and therefore they take advantage of their large size. Now you can imagine this is not entirely trivial. The idea, as I just described, it doesn't seem too crazy, but implementing it is, altogether a different story. So this all started back in the 50s, actually. The first idea of creating a compensation system for the atmosphere goes to an astronomer named Babcock back in the 50s. It was starting to be built in the 70s, a little mechanical mirror, a 6-element mirror that someone had to manually push and pull. Believe it or not, there were two astronomers, one at the eyepiece and the other one manipulating the mirror. And the one at the eyepiece would tell the other one, oh, push number 2 a little bit up and number 3 a little down, something. And they would see the image get crisper or worse, depending on which way they were pushing and pulling. Obviously, they were not doing that every millisecond. It was a much slower process. So it wasn't great, but it was a demonstration it could work. And since then, astronomers have worked hard. Back in the late 80s, some French colleagues of mine built one of the first astronomical adaptive optic systems. The military had done some of that a little bit before that. And by now, it has become very common to all large telescopes to have their own adaptive optic systems, sometimes guided by a laser, as shown here in the image from the Lick telescope, the Shane telescope at Lick Observatory. But now it's commonplace to have adaptive optic systems. So large telescopes with adaptive optics on the ground can afford or can provide the resolution we need to separate out a star and a faint planet right next to it. It just gives us enough resolution to do that. So that was the first step. Now, along the way of adaptive optics, we've developed a lot of technologies to improve, in particular, the deformable mirror. It was the most challenging part of the whole chain, if you will, of adaptive optics. And nowadays we have microchip mirrors, we have mirrors that are the size of secondary mirrors. This probably is, let's see, pretty close to the size of your Mount Cuba 50-inch telescope. It's actually the secondary mirror, I believe, for the one of the two LBTI telescope, although I'd have to double check. So we know how to make adaptive optics with very small and very large deformable mirrors, and they're proven very, very powerful and reliable. Now, indeed, adaptive optics is now used in many, many fields in astronomy. These are just a handful of examples. They're all on, off, or with adaptive optics, without adaptive optics, images of the moon, Neptune, the sun, binary stars. And like I said, adaptive optics is completely commonplace. In fact, it's so commonplace that it's now been exported to fields outside of astronomy. And adaptive optics is being used to image the back of people's eyes, the retina and the cells in your retina, or to image living cells and study them as they are evolving and getting sharper images of the interior structure of cells. So the technology has moved on to other fields beyond astronomy. But of course, for today, I'm just going to stick to astronomy. So going back to our problem of finding the firefly right next to the lighthouse, we start with, this big booming bright star in the center. We use adaptive optics, and what it does is it tightens the beam of the lighthouse. So it's a lot better, but it's still far too bright. You still don't see the firefly. Now, if you want to see the firefly, if this was a real lighthouse, you would just find the plug and pull it off, or you put it in Texas and it would just be out of power right now. Either way would work, and that would be the end of the story. But of course, in astronomy, we can't just ask a star to just turn off so we can see the star next to it. Not to mention that a lot of these planets are only bright because there's a star that's shining on them. So we don't really want to do that. So instead, we use another method. We put a mask. We just block the star, and we hope that the firefly, or in our case, the planet, is not just behind the mask, but a little bit off the mask so we can actually see it. Now in astronomy, this mask is called the coronagraph. And that's a very old technology again, as far as astronomy is concerned, modern astronomy is concerned, because it dates back all the way to the 30s. We're almost 100 years ago now. French astronomer Bernard Liot invented it because he was interested in studying the corona of the sun, and he didn't want to wait for the next solar eclipse and have to travel halfway across the world. He wanted to be able to use his telescope as often as possible. And so he created a mask to block the sun so as to study the corona next to it. Now, a lot later, astronomers realized they could do the same thing, just change the size of the mask, basically, not cover the whole half degree that the sun is, but something much smaller, to block out just one star and see what's next to it. And this was illustrated here in this just one example of Sirius, the brightest star in the sky, which would have been where the white star is in this diagram. A circular mask has been placed on it. There's a little bit of light that has leaked out, but more importantly, you can now see the faint companion to Sirius right down here, the little white dwarf, very famous white dwarf companion of Sirius. And this companion is 10,000 times fainter than Sirius itself. And you can see it pretty easily in this particular example. Of course, without the coronagraph, it would have been impossible to pick it up, just too faint right next to a very bright star. So the combination of adaptive optics on large telescopes and coronagraphy is what has led us to finally, after many years of development, the possibility of detecting planets around other stars. Now, the modern combination of these things end up being things that are the size of fridges or small cars, depending on who you talk to, or piano or something like that. Here is one instrument on the left here, this blue box down at the bottom, dark blue box, is the so-called Gemini Planet Imager that I've been involved with over the past 5-6 years or so, installed on the back of a 25-foot telescope down in Chile. In another telescope on a similar size mirror, which is the circular mirror you can see on the left-hand side of this picture here, this is an equivalent instrument called Sphere that European astronomers are using to do the same kind of studies as we do with GPI. Again, GPI stands for Gemini Planet Imager, so you can see we've designed it specifically to combine adaptive optics and coronagraphy to detect planets around other stars. So we've devoted a lot of efforts in developing the instrument and then in conducting a large survey with it so as to try to find as many planets as we can. Nonetheless, even with this quite advanced technology, it remains a really hard task. Here's an example. On the left here, this one image that you can see is one image of one star. And the star would have been in the center where the red star is located. You can see the sort of circular mask around it where it's a little bit darker, the dark blue region here. And everything else, anything you see in here, it's an artifact or residual due to the imperfection of the instrument. A handful of things in there are sort of on purpose, but most of it is unwanted. We would have wanted this region to be entirely dark so that we could see very easily a faint planet in it. Well, believe it or not, there is a planet in that image, but you would not be able to find it. To find it, you need to, first of all, combine quite a few of these images. We typically take sequences of maybe 40 such images, spend an hour on the object or something like that. And then we combine them doing a lot of post-processing. I'm sure many of you do advanced processing of your pictures of the sky that you take of your favorite galaxies or nebulae or whatnot. We do the same thing with our data, and we end up getting something that looks like this. By combining all these images, the star is still here hidden in the center. We still have our little mask here that's blocking the star. but now we can see the planet right down here. And that little object, right now you don't know it's a planet, I'm just telling you, but that object is 500,000 times fainter than the star itself. And it is just about 1 or 2/10 of an arc second, this 1 penny at 25 miles resolution we were talking about earlier today. So you can see that these advanced instruments finally achieve the performance we need to find objects that are planets around other stars by combining adaptive optics and coronagraphy, but also putting lots of signal processing behind it to combine it. Now, this is just one example. I'll get back to this one system a little bit later. But before I do that, let me show you a little movie that summarizes pretty much, 4.5 years worth of studies with this same instrument, the Gemini Planet Imager that we've taken in Chile. And this is going to be a movie where every one snapshot is one star we studied. And it's sort of the final image. It's kind of funky looking because of the way we process the images, but in every time, every image, the star is at the center, it's hidden behind the mask, and you want to look somewhere around here to see if you see anything that looks like a point source. So I'm going to play the little animation. It's actually taken in order in which we observed, going very fast because there's 500 stars or something like that. And I don't want to focus on any one in particular. But the first thing is, when I play this fast, it's hard to see much. There's not much happening. Once in a while, there's something that pops up. Usually it's a binary star. There was a little companion we didn't know about. We took images of it. But most of the time, there's just nothing. A handful of times, there's some weird fuzzy structure. I'll get back to it in a second. But the bottom line is, out of 500 stars we looked at, very, very few had something we would call a planet or close to a planet. So we were kind of like a little disappointed because we were hoping to find lots of planets, of course. But in fact, there's a lot of information to gain from this sort of dearth of interesting objects in there. I'm probably not going to play the movie all the way to the end, although we're almost there, so I might as well. Just wait until it finishes. And at least I hope we'll give you the sense of how many stars we looked at. 500 stars is a lot of telescope time. We spent, like I said, 4.5 years, the equivalent of probably 90 to 100 nights worth of telescope on one of the largest telescopes in the world. It was a big campaign for sure. So some of you might have spotted here and there, floating in there, some weird fuzzy objects that would have been some of these. Those are objects where the star is always in the center of these frames, but then there's extended structure. And what we're seeing here is not planets, but it's belts of material, sort of equivalent to maybe our Kuiper belt in the solar system. We're not seeing the comets and asteroids that form that object. What we're seeing is the dust that is produced by the collision of these objects. And as they produce dust, that dust can scatter the starlight, and we take images of the scattered light as we see in here. Now, I'm not going to go into the detail in this diagram here. That's more the part I'm actually interested in that survey and more actively doing research. But we're studying the shape and structure and size and morphology of all those disks, because they sometimes tell us something about planets that we don't directly see, but that are affecting objects around them, just like Neptune is carving out the inner edge of the Kuiper belt, for instance. Now, as far as finding planets, once we've looked at 500 stars, astronomers love to boil that down into a very simple diagram like this. And it probably is one of the most boring diagrams we can make out of a survey like this, but I just want to walk you through just to give you an idea of what we've done. So in this diagram, the horizontal axis is the distance, or some major axis of the objects that we find next to a star, and the vertical axis is its mass in units of the mass of Jupiter. And each little red circle here, those guy here, here, and up here, is an object that we found around one of these stars we looked at. And the color coding here indicates where we've been most sensitive to. So in this blue region in the center here, that's where it's easiest for us to find objects. And we did find a few. And as we push down towards the yellowish color down here, it barely could find anything because very few stars were amenable to observations in that region. So the first thing to say is, out of these objects we found, we typically found two categories of objects: brown dwarfs and planets. So around stars, we don't just find planets, we also find brown dwarfs, those sort of failed stars are just too small to really be stars. They will never burn hydrogen into helium, but they sometimes end up being companions to stars as well. We did find a few of those. Those are not very interesting, at least for tonight's presentation. So I'm not going to talk about those. I'm going to focus on the planet side of things. When the planet side of things, if you look at where the objects we found are located, they're located at several times the mass of Jupiter. So they're kind of like quite large planets. In fact, if I put Jupiter and Saturn in this diagram down here, they're way lower than what we can detect. We don't yet have the instrumentation to find a planet like Jupiter or Saturn. We're pushing the current instrumentation to get there, but we're not there yet. The other thing is, remember we looked at 500 stars, and there's only a handful of points in this diagram. And it's not because we're hiding lots of discoveries that we want to claim and make big press releases out of it in the next few months. It's because there's just very few of these things. Very massive, puffy planets, multiple times the mass of Jupiter, are just rare around other stars. Just a few percent of all stars have planets like these. May not be so surprising. It's hard to imagine how to form such a large planet in the first place. But it goes to show that as we improve instrumentation in the future, and we keep pushing down on these curves and push down towards where Jupiter and Saturn are located, we're bound to find more and more planets because there should be a lot more of these smaller planets. So we're still partway through to imaging planets like those of our solar system, is sort of the message to get out of this survey. Now, rather than talking about the survey here, I want to go back to some remarkable system and take you through a little tour of the most exciting systems we've looked at over the past 10 years or so. So the first one I'll tell you about is one I showed you an image of earlier, so-called HR 8799. Nice phone number if you want to fall asleep with star names. But the point is that this is a star right here in the center, a little mask around it as usual, and then 1, 2, 3, 4 planets. But the fun part is those planets are actually moving. And if I play you an animation, now you can see the orbital motion. You can see these planets going around this star. And you can even see that the planet that's furthest away, this one out here, is moving a lot slower than the one closer in, just like in our solar system. Because of course, all these planets obey the same Kepler's law that we are familiar with in our solar system. So we can finally observe what these orbital motions are. And as it turns out, it's been identified that these planets are actually on eccentric orbits, like Mercury, or maybe even more eccentric than Mercury, somewhere between Mercury and Pluto's in our own solar system, which is interesting because it's hard to make multiple planets go around the star on eccentric orbit and not get them to hit each other or perturb each other for a long, long time. So this is an interesting system to study from the dynamics perspective of planetary systems. And I should mention, each of these planets is, again, a few times the mass of Jupiter. So they're quite massive in their own right. Another interesting system is the one I showed you before, when I was talking about the very high contrast, about 500,000 to 1 contrast. That planet around stars, so-called 51 Erie, is actually a pretty good solar system analog. We estimate the mass of the planet to be only twice the mass of Jupiter, which is pretty low by our modern standards of finding planets. And it's on an orbit that's the size of which is comparable to Uranus's orbit. So we're talking about solar system scale and solar system mass kind of planets. Now this one is also eccentric, so it's not on a circular orbit like Uranus. And we're not entirely sure why we're finding a lot of eccentric planets, but clearly there is an indication that not all planets go in perfect circles like they do in the solar system. That's food for thought, let's say, for the future to try to interpret and understand those eccentricities. Interestingly, for this particular planet, we've been able to take a spectrum. Remember our goal of taking spectra and looking at the composition. And what we found is the main molecules that are made up, that are making up the atmosphere of this particular planet are methane and water, which are the kind of molecules you find in the solar system. So not only is this particular planet similar in orbit scale and in mass scale, but also in composition to the planets of our solar system. Now, another interesting system, I'm going the wrong way, excuse me. Another interesting system we've been looking at is the Beta Pic system, Beta Pictoris, a planet, an object where, first of all, a disk of dust, as I was talking about earlier, has been identified for over 30 years now. And more recently, a planet has been found. Again, you have an animation in the bottom right showing that we've been monitoring the planet as it went from one side of the star all the way to the other side and coming back on the other side of the mask. Been able to wait for it and see it come back. And in fact, more recently, a second planet has been found even closer in. So now we're seeing a system where planets and dust disks interact, much like planets and asteroids and comets interact in our solar system. So again, sort of an analog for a solar system, although the primary star in this case is about twice the mass of the sun. Speaking of disk, here is another intriguing system. Again, another phone number I won't even read this time. Down at the bottom here, there's actually a binary star behind the mask. Here is the little mask, and behind it is actually a very close binary star that you cannot really resolve. And around it is this sort of like ring of material that you see here, orbiting around the binary star. And yes, we know of planets around binary stars, so it's not surprising that this happens. What's actually interesting about this system is that if you extend your view a little bit further away, you find that there is another planet, or there is a planet in the system. It's actually quite far away. It's more than 20 times, or it's about 20 times the orbits of Neptune, so much, much further away from the star. And not only is this planet very far away from its host star, or host binary star, if you draw simple lines as to the orientation of the disk and the star to planet orientation, you see there is a big angle between those two things. Much like Pluto is on an inclined orbit, this object is on a highly inclined and highly eccentric orbit that has just been mapped out by some colleagues of mine just a few months ago. And so what we think happened here is that there was a planet that formed along with this disk way down here somewhere. And somehow, maybe because of the binary, maybe because there is another planet, that planet got kicked out into a much higher and further out eccentric orbit somewhere in the past. How and when exactly that would happen is subject to interpretation. Now, if we go back in time, what we're interested in finding stars that are currently forming, not just already formed billions or millions of years ago, but as soon as we can find them. And here is a pretty messy picture of a young star called PDS 70. And again, the star has been masked with a little chronograph here. And there's lots of stuff around it. That's the dust and gas out of which that formed along with the planet. And in the middle of that, somewhere in there, is a big bright planet right next to it. So we think this is an adolescent planet, probably a giant planet like Jupiter or larger or more massive, but it's still in its parent disk, interacting with it, and we can study that. And we think this system is just a few million years old, somewhere between 5 and 10 million years old. So very, very young, at a phase where in the solar system, the major planets were forming, the terrestrial planets were probably not quite formed yet, or just about. And so this is really an interesting and exciting system to study in the future. In fact, there's hints of another planet in here. We're not quite sure yet. Now, one last thing I'll mention, because it was in the news, I think, last week or a couple of weeks ago, and some of you might have heard about it. This is not a great figure. I just grabbed it from the paper that was published. Some colleagues of mine were studying one of the closest stars to the sun, Alpha Centaurus. And using a pretty complex but similar kind of instrument, they were trying to find planets in the habitable zone of that star. Now, most of the planets I showed you before, they're quite far away. They're Uranus orbit, Neptune orbit, things like that. So you're not in the habitable zone of these planets, of these stars. But in this particular case, because Alpha Centauri is so close in, if you find a little faint thing, as this little blurry thing down here, it's close enough to the star that it would be in the habitable zone. In fact, some of the models they use suggest something like a Neptune-type planet. However, I was on a call, when was it? Just yesterday, in fact, where the main author of this article was giving a presentation on this. And it was very clear that he doesn't really believe this is a planet and is subject to discussion as to what that is. But the point is, we're getting to the stage where, at least for the closest stars, we can use these methods of adaptive optics and coronagraphy and post-processing to find planets that are very much like those of our solar system, and even in some cases in the habitable zone of those stars, which of course are exciting for the prospect of life around on these planets. So let's see, it's about 6 o'clock, so it's time for me to wrap up. I'll just walk you through what we're expecting as a field, how this is going to evolve in the next 10, 20 years or so. We're going to keep trying to do the same thing, but we just need better equipment. We are limited in part by the size of our telescopes, and of course, we're looking forward for the next generation of the largest telescopes, the so-called extremely large telescope, 30-meter telescopes. Those are going to be 3 times larger than the ones we have right now, and therefore we'll be able to find planets 3 times closer in. That's great, and not only that, but because it's much larger, it collects more light, we can find fainter planets, therefore smaller planets as well. Those should start to come online some point in the 20s, although with the pandemic, everything has got delayed, of course, so I'm not exactly sure when, but somewhere in the mid to late 20s is when those telescopes will start getting online. We're also making progress in space. I mentioned that we'll be launching James Webb later this year, and some of the science that will be done with it will be to try to do the same thing I was just talking about today. Although not all the instruments have been, let's say, designed specifically for planet finding, they have the ability to find some planets, and we're sure we'll be using that. Later down the road, at the end of the decade, probably we'll be launching the Nancy Grace Roman Space Telescope. It's about the size of Hubble, but it will have a core instrument dedicated to the finding of planets around other stars, whereas Hubble is just a generic instrument. It's great, it's fantastic, but it's not been designed for such a challenging task as finding a planet next to a star. The Nancy Grace Roman Telescope will have an instrument dedicated to that and will be therefore much more powerful. In the upcoming decade, we hope to launch the next generation of missions. We're not even quite sure as astronomers which one we really want. People advocating for missions named ABEX and LUVOIR. But the spirit is we'll still want to use a mask, but we might even use the mask to be outside of the instrument, as in this star shade illustration here, a giant flowery looking kind of thing that will mask out the star and the telescope sitting behind it, taking the picture of the planet right next to the edge of the mask. And this is much more powerful than having a mask inside the instrument. Just much more challenging, you can imagine. You need to line up these structures that are thousands of kilometers away from one another. It's not an easy task either, but that's the next generation. And then who knows, someday, maybe 100 years from now, we might be able to dream and think about something like the so-called asteroid belt astronomical telescope. There was something that came out in Physics Today a few years back when they were having their century year. And they asked people to invent what physics and astronomy will look like 100 years down the road. And someone had come up with the idea of using carved and polished asteroids on the asteroid belt itself, collecting all that light into one tiny place, and using the fact that you're effectively using a telescope the size of the asteroid belt to be able to get great detail and take pictures like the one on the right here, obviously a simulation of an Earth-like planet around one nearby star. But you do have to remember that if you want to actually see the details of the planet to that level of precision, you will need a telescope that size. So it is a big challenge way down the road. So I'll leave it there with that little animation of the orbits of the planets around HR 4799. I hope you enjoyed, and I'm very happy to take any questions you might have.
Awesome. Gaspard, thank you very much. Could you talk a little bit more about exactly how the masking is done? I'm picturing, like, when it's nighttime and a car is driving towards you and you'll, put your hand up to block the light, but that feels very crude compared to what I imagine you have to do with the telescopes.
It's not that bad, actually. It's sort of the spirit of the star shade, in fact, where you do put that way out there. It's a little different inside of an instrument, but it's the same idea. So you imagine in your optical path, right, you have the light bouncing off your primary mirror, maybe a secondary mirror and whatnot. And at some point, you might have a focal plane where you might put your eyepiece, or maybe there's a first focal plane and a second focal plane. Right? So in the first focal plane, you'll put a little mask, just like you said. You just make a little round circular mask, you put it there. Now, because of diffraction, you do have to use something called a Leo stop. That's where Bernard Leo came in, somewhere in a pupil plane, a conjugate plane to that, to block out refracted light off the edge of your mask. But that's essentially the spirit of coronagraphy at the 0th order. Now, the modern version of coronagraphy uses some fancier techniques where we actually create or place microdots, dark microdots inside of something like, a lens or something like that. And we use the density of the dots to make the glass be either opaque or transparent. Like the higher the density of dots, the darker it gets. And we can have a smoother transition from completely opaque to completely transparent, which is a little bit better because it reduces the effect of diffraction because you don't have sharp edges. But it's just a revision of the same thing. There are some more fancier ways of doing the masking using holographic techniques, using phase shifting, and using the fact that if you find a way to take the light, take its opposite phase and combine it with itself, it cancels out by the magic of interference, of destructive interference. So you can use that method as well. And there is some success. It's a bit harder with the atmosphere because everything's always changing and moving all the time. So it's a bit harder. And in a sense, the simpler mask is actually the most effective way.
And I guess you adjust the diameter by just moving it forward or backwards in the light path, right?
Yeah, so what you do is you basically decide ahead of time. In this kind of instruments, we've sort of have a fixed diameter. But let me rephrase that. We have a fixed diameter for a given wavelength of observation, because we want to match to diffraction, and diffraction is a function of wavelength, right? The larger the wavelengths, the larger the diffraction patch. So what we end up doing is having a series of filters, much like of masks, excuse me, and then we have them on a wheel, just like with a filter wheel, basically. And you just change that. So we don't move them in and out. We just have a series of them, and we just select, oh, I'm at wavelengths this, so I need this mask, and I take this position.
Because I mean, I imagine you want the diameter of the mask to be big enough to block the light, but not much bigger, because then you start blocking the planets as well, right?
That's exactly right. That's exactly right. So basically what we do is the diameter of the mask, let's say, is about twice the resolution of the telescope. So we take all the light of the star, and even with adaptive optics, even if it worked perfectly, which it never does, but even if it were, all the light would still be spread out over an area that's essentially the diffraction size of the telescope, given by the ratio of wavelengths and telescope size. So we take our mask to be about twice that. And there is some argument between people that 1.5, 2.5 is better. But yeah, the compromise is you want to mask as much as you can, but you don't want to mask too much, because then you don't see anything around, because you can only find planets at like thousands of AU, and that's not as interesting, of course.
Cool, thanks.
Gaspard, I had a question. So first of all, fabulous talk. Thank you so much for that. And also thanks for agreeing to just give this talk in the first place. So I really appreciate that. I think everybody else does too. Yeah, by the way, so I auditored a class that Gaspard taught last semester at Berkeley, which is how I found out about him. And you know, a fantastic lecturer and obviously brilliant guy. So it's really been a pleasure to go to his class and learn from him and be intimidated by his brilliance and how smart all those students are. Oh my God. I had a question. So there's a couple methods for detecting exoplanets. One of them, I guess, is looking at Doppler shifts and detecting motion in that way.
Yep.
And another is
transit.
Is transit light curve, as you did
Yep.
as we did in class. Are there any cases where the data that you got, that one gets from those two techniques, are contradictory, or have they always been confirmatory?
Contradictory.
In other words, where the period is wrong based on, you know, the periods are different, or there's some other stuff that doesn't quite compute.
No, I would say they're more complementary most of the time. So the spirit is that because the Doppler method relies on the gravity force between the planet and the star, you get a sense of the mass of the planet. But because the transit method relies on blocking the starlight, you're measuring the size of the planet, like the physical size. And so you can use the combination to get something like the density of the planet and say something about what kind of planet you're looking at. So in that sense, they're complementary.
I guess what I was wondering is like whether there's any cases where a light curve was established and looked like a planet, Doppler measurements were made which were not in accord with that, and then it was determined that the light curve was really attributable to something else.
Yes.
Like
so,
a dust disk or something like that.
Yes, but mostly because of the telescopes we're using. So the main case where this happens is because what you're looking at is a star, and then you're getting the brightness and you see the regular deeping, and it comes back and comes back and comes back. So clearly it's a signal, it's astrophysical, it's not instrumental or anything like that. But what you're looking at is a star that does not have a planet, but right next to it in projection, but probably further back in the sky, there is an eclipsing binary.
Mm-hmm.
And eclipsing binaries do the same thing, right? They go around each other and they block one another. That's why they're eclipsing. And now, of course, if you just look at an eclipsing binary itself, the dip that the eclipses create are huge. They're like tens of %, right? The star goes a lot fainter. But if you have a bright star in front and a faint-ish eclipsing binary in the background, it looks like a 1% perturbation, 1% perturbation on top of a bright star that you could think is a planet. That's the main cause for false positives. So it's a real astrophysical signal, but it's not a planet. And the reason we get fooled by these is like missions like Kepler or now TESS are designed to do very precise flux measurements, photometry. They're not designed for doing resolution, and they have incredibly large pixels. I don't want to say a number because I'm going to get it wrong, but individual pixels on Kepler are multiple arcseconds across.
Wow.
So in one pixel, you're bound to have more than one star, at least sometimes. And therefore, what often happens is once they have a candidate, what usually happens when they have a candidate from Kepler or TESS, the next thing they do is they take an adaptive optics image with a ground telescope to just see, is there another star right next to it? Because that might be the eclipsing binary right there. And if they don't see any star in the background, then they can tell it just can be a planet. Now it doesn't work anymore because I would see the background eclipsing binary. So you need that follow-up to sort out the most likely planets from this kind of like false positives. In fact, the diagram I showed you before with the few thousand planets, the vast majority of the transit planets in there have been now identified as bona fide planets because there is no such star in the background that could mimic the same signal.
Interesting. Yeah, okay, that's very good.
Gaspard, as a follow-on to that, would you mind jumping back? It was one of your earlier slides where you showed the number of, a bar chart of the number of discovered exoplanets over time.
Absolutely. Yeah. That was a lot of information. Getting there. There you go.
Cool. So yeah, so I get the red and the green. Now that we've kind of come full circle, could you maybe talk about the purple and the blue and the yellow and some of those smaller ones?
Yes. So unfortunately, I don't have the figure without the, I blocked out what the other colors are, so I'm going to get wrong what the methods are. But one of them is imaging, and I suspect it's the purple, given, it might be the blue actually, the dark blue, the next to last up here.
Okay.
I think that's the imaging. The purple right next to it, that's the microlensing method. So you're probably familiar with gravitational lensing, of course, where light is bent by presence of a mass and so on. So microlensing is a method where you look at a distant star and you wait until something passes in front of it. And if it passes right in front of it, it's going to create the same kind of deformation of the image. But it's too small for you to resolve, so you don't get an image of that. But along with that, you get an enhancement in brightness. So the stars become a little bit brighter for a few days or a few weeks. And when that happens, you know that something passed in front of something else. But occasionally, there's something that passes in front or the star in the background. Either way, either one of those stars has a planet next to it. And then in that phenomenon, you get an increase in brightness due to the star passing in front of the other, and then a secondary bump due to the planet. So they start to find planets this way. And that's the microlensing method. So that would be the purple. And then I believe that the yellow, if I'm not mistaken, is some sort of timing method, where you look at any phenomenon that is related to stars and that has a very great regularity, like an orbit, for instance, but you measure when that orbit is happening, and you see that there is some deviation back and forth around a perfect periodicity. So you're looking at what we call timing variation. So for instance, if you have a transiting planet, right, it comes back every 5 days, let's say, okay? So every 5 days, the planet comes back. But sometimes it's 5 minutes early, sometimes it's 10 minutes late, and then 5 minutes early again, then maybe 10 minutes early, and then 5 late, and so on. And there's some variations around that. And that shouldn't happen. If you have a star on a planet, that will not happen. It will happen with perfect regularity. There wouldn't be this deviation from periodicity. And the interpretation of that is that there is a second planet, or some other object anyway, that is in the system, and the mutual interaction between that object and the planet is making the orbit of the planet go a little bit ahead, a little bit behind. Much like Mercury's precession, although in that case it's because of general relativity. But any kind of timing variation like that would infer the presence of a third object that you don't see directly or even indirectly, but just through timing. And transit, as so the byproduct of transit is once in a while to find these transit timing variation systems, where you can say there's a few more planets here, at least one more, and you can even infer the mass and period of that planet from the transit variations. So those are the main methods.
Okay, so do I pull out from this graph that the direct imaging of exoplanets really started in the mid-2000s, like 2004, 5, maybe in there?
Pretty much. I think
I didn't realize it was that long ago.
Yeah, it's not that long ago. It took, easily 10 years after the first discoveries, obviously, of planets. And even then, I think it would depend which astronomer you ask the question to. Because the first 2 or 3 that were found were systems where you had an object that was kind of a very low mass brown dwarf, maybe a high mass planet sort of at the edge, and itself was orbiting not quite a star, but maybe a brown dwarf or something. So it looked more like a binary star, but both masses very reduced, but they're kind of comparable in mass. So do you want to call that a planet, a planetary mass object, low mass binary kind of system? It's kind of debatable. I think the first bona fide planetary systems probably came up in about 2008. And that would actually be the system with the 4 planets I was showing the animation of.
Gotcha.
Those were clearly just about 5-6 times the mass of Jupiter. They're clearly planets and not brown dwarfs.
Gotcha. Cool. Actually, I thought it was more recent than that. So I didn't realize we've been doing it for that long, surprisingly. So cool. Okay, so I guess at this point I would like to open it up for as long as Gaspard is willing to tolerate. If people want to unmute and ask some questions directly, it's nice to hear some other voices.
I've got a question.
Go ahead.
I was wondering what type of materials are the adaptive optic mirrors made of? I mean, how can they be like flexible and still have a polished surface for a mirror?
Well, the original ones were about, let's say 10 centimeters-ish in size. They were actually just glass, some sort of, I don't know which glass exactly, so I wouldn't be able to tell you, but just thin enough that you could push and pull. Obviously thick enough that they wouldn't break, so there's obviously a compromise there.
Mm-hmm.
But if you make it thin enough, you can actually push and pull. Now, the thing is, you only need to push and pull by about a micron or a couple microns. So it's really not that big of a pull and push.
And that was also
difficult.
That was also bringing up, so you were saying that the smaller wavelengths obviously have less diffraction. So when you're trying to image these, do you use basically the whole visible spectrum to gather as much light as possible? Or do you try to only use the smallest wavelengths that are usable? So like ultraviolet or close to the blue end of the spectrum?
So it's a difficult compromise, let's put it that way. The shorter wavelengths you go, the tighter the diffraction is because of the laws of diffraction. However, the harder it gets to fight against the atmosphere because the transmission and the blur that the atmosphere introduces gets larger and larger as you go to shorter wavelength. Kind of the same reason why the sky is blue and not red, for instance.
Mm-hmm.
So going too short wavelengths is a challenge. Going longer wavelengths, you lose in resolution, but most of the adaptive optics technology I showed you, and the images I showed you today, were all taken in the near infrared, somewhere between 1 and 2 micron typically.
Okay.
We do push them a little bit in the optical, but it's a bit harder there. The other thing is that it does depend on the post-processing method we use. Some methods, we like to have as much light as we can, and we take a broadband as broad as we can, basically. Some other methods are better off using a very narrow band. And ideally, what we do is we take 2 wavelengths right next to one another, because then anything that has to do with diffraction is almost the same in both images. But the planet might be different because it might be brighter in some wavelengths than in some others. And so we can hope to subtract off what is the residual of the starlight that's been diffracted and keep up the planetary signal, basically. So it does depend a little bit on the post-processing methods.
Interesting, thank you.
Mm-hmm.
Yeah, how long an exposure do you need for the infrared spectra of planets?
So let's see. You may remember the spectrum I showed you about these 2 Jupiter mass planets, the sort of solar system analog that had the methane and the water vapor in it. I believe this was about, I want to say the equivalent of 7 or 8 hours of telescope time on Gemini, but there's a lot of overhead, meaning time taken not actually acquiring data, but pointing and adjusting and all that stuff. So the effective time might be more like 4 hours-ish to get that spectrum, which is pretty good. If there wasn't the star next to it, if we could magically take the planet and move it in a place where it's a dark part of the sky and just take a spectrum of that, we could do that in like half an hour. Those planets are not very faint in their own right. They're actually reasonably bright. The challenge is that they're sitting right next to something that's really booming bright. Mm-hmm. And so it's the disentangling of the two that requires a lot of telescope time.
Okay. Is there any potential to get high resolution visible or UV spectra?
There has been a couple of cases where we've done high resolution infrared. And by high resolution here, I mean something around 10,000 resolution. So that's pretty high spectral resolution by our standards. There are some instruments that are in design phases, aiming to go into the optical. The UV, I think, is pretty much hopeless until we can put that onto a space telescope that's optimized for UV, which, for instance, James Webb is not. It's infrared specific. So the UV from the ground is just very, very difficult. There's a lot of information there in principle, molecule-wise, for analysis of composition and whatnot. The experience of the few systems where we've been able to make spectroscopy, though, shows that in the UV, we tend to pick up Rayleigh scattering of probably AZES, is our best guess, maybe clouds, but most likely AZES. And that tends to wipe out any sort of molecular feature that you would hope to find in principle with UV spectroscopy. So it's not even clear that scientifically that's the best first thing to do, let's say.
Right. The thing that occurs to me is that if you can take a direct spectrum of planets, and particularly if you get down to smaller planets, our own planet has a spectrum, has a spectral signature that's characteristic of semi-intelligent life. Okay, if you look at our planet from space, what do you see? You see light pollution. You've got, mercury emission lines, sodium emission lines, a few other things. If you can take direct spectra of planets in the visible, there's the possibility of detecting those same signs of life that we're putting out.
Absolutely, and again, it's a technical challenge primarily, but I totally agree with you there. There's also lots of molecules that are detectable in sort of the red part of the optical, dioxygen, ozone, and several others that are mostly abiotic, so not representative of life, but there's a lot of biochemistry and astrochemistry studies and astrobiology studies to try to identify some more trace molecules that might be only possible, at least on Earth, from life to be searched for. And again, the sort of the sweet spot from the instrumentation and technical side is somewhere between the red of the optical and the 2-micron kind of window. That's our best guess for what we can achieve, let's say, in the next 10 years. Obviously, 50 years down the road, we probably can do better than that. But in the sort of like relatively near term, we're kind of like focusing on that wavelength range for technological arguments primarily.
Okay, thank you.
Gaspard, you might already have mentioned this, and I'm sorry if I missed it, but out of all a gazillion stars, how do you choose your candidate stars to really look for these detailed observations?
There's a star picker that we developed for our survey, for our specific survey. Other surveys have done something similar. One thing I did not say is that the planets I showed you images of, they're all not seen in reflected light, but in their own thermal emission. They're hot enough because they're young to be quite warm still, several hundred kelvins, and they emit in the near infrared. And that's what we actually detect rather than reflected starlight, like you would see the Earth from the distance, for instance.
Interesting.
And so that pushes us towards observing very young stars, because the younger the star, the younger the planet, obviously, and that means the warmer it is because it still has a lot of heat accumulated from the formation era. Yeah. And that makes it easier for us to pick that up. So we try to find the youngest, closest, brightest, because it helps the adaptive optics, and most solar-like kind of stars. It's sort of our set of criteria, besides obviously being up in the sky.
Most what light?
The most sun-like.
Oh, sun-like, okay.
Yeah, because we're kind of like, sun-centric.
Sure.
Although in practice, what I did not say either is that most of the planets we found so far in these kind of surveys, and I don't want to say that our survey, just all surveys, were found around stars somewhat more massive than the sun, between 50 to 100% more massive than the sun. Around solar-like stars, we still haven't found something like a 2 Jupiter mass planet, for instance. They're probably out there, we just haven't been able to find them.
Are they all main sequence stars?
Most of them have not quite reached the main sequence, or just barely.
I see.
So they're quite young as far as stars go.
Yeah.
You mentioned earlier that a lot of these, or a few of these solar systems, a lot of the planets had eccentric orbits. Could that be, not an issue, but a result of basically this whole solar system being young, and basically the orbits not having enough time to stabilize?
It's possible. I think it is more likely that if you let a planetary system with multiple planets in it and all sorts of stuff around it, if you let it evolve over time, it's more likely to get more and more eccentric rather than less and less eccentric. And the reason for that is the most effective way of sort of circularizing is the word we use, the orbits, making them from ellipses to circles, would be to use the big massive gas disk out of which the planets form in the first place. So very, very early on, this could happen, that they would stabilize. But those kind of disks only live for about a few million years. And after that, there's just not enough material to stabilize anything. If anything, if you have multiple planets, at some point they might end up getting into situations where they disrupt or perturb one another into more eccentric orbit rather than more circular orbits. So it's unlikely to be the explanation. It is possible that in some cases, the planets are eccentric precisely because they were interacting with one another and they kind of like they're nudging one another slowly but surely. It is also possible that in some cases, they were formed in a more, let's say, violent or dynamical kind of process rather than this more sort of smooth, slow process we think the solar system went through. And so because it was more chaotic, it naturally led to more eccentric orbits. So it might be just a leftover of the formation period. There's an outside chance that recently some other star passed by and sort of kicked out the system and some of the planets got into eccentric orbits. We think that's a likely explanation for the one planet I talked about at that was a very distant sort of like incline at a weird angle kind of planet. This one we think was interacted with another star that passed through something like 10 million years ago, something like that. I don't remember the exact number on top of my head now. So that might be an effect there.
I have a question. You mentioned a few moments ago that you're looking at young stars. Does that mean you're looking mostly at open clusters?
We are looking as young and as close as we can. And it turns out most open clusters are a little too far away for us because when the stars are sort of like, let's say the Pleiades kind of distance, they're quite a bit fainter than what we would like for the adaptive optics. Remember, the adaptive optics has to sense this blur of the atmosphere and refresh every millisecond. To do that, we need a lot of light every millisecond. So we need pretty bright stars. And so the Pleiades distance, it starts to become a problem to do that with great precision. The other thing is, at these kind of distances, Pleiades, you're talking something like, what is it, 400 light years away or something like that. The angular size where the planet would be next to the star becomes smaller and smaller and smaller as you go further and further out. So ideally, our sweet spot is something like, 100 light years or less, basically. So quite a lot closer than the Pleiades. We've looked at some Hyades star, which are a lot closer, but those are a lot older. They're kind of youngish. It's still an open cluster, but it is in the 600 million years, 700 million years old. And for the planets we are hoping to find by their own thermal emission, that's pretty old. By then, it's very weak emission. So ideally, we find something that's 20, 30, 40 million years at most. And so we've built up catalogs of smaller groups of stars that would be kind of an open cluster, but much smaller in numbers. We call them young nearby associations, like the TW Hydra Association, the Beta Pictoris associations. And those are typically in the 50 to 100 light years away. And they're somewhere between 10 and 30 million years old. And they're more favorable because of both of these arguments than any open cluster we know of.
Thank you very much.
Could you talk a little bit more about how your adaptive optics works on the Gemini?
Sure. Well, it kind of depends. Maybe you have a more specific question about it, or in general?
Are you using an artificial star, or are you sensing the light from the star itself that you're studying?
Yeah, we're actually using the star itself. I mentioned the use of laser to sort of like laser guide star, artificial star guiding for adaptive optics, which has been a great, tremendous progress for all sorts of studies of faint objects in the sky. But when we have a bright star, we'd rather use the bright star rather than laser. And the reason is a little bit technical. I probably don't want to go into great detail here. Maybe we can have an aside or an exchange later. But with the laser, you can create an artificial star at a very high layer, typically the sodium layer, about 90 kilometers up in the atmosphere. And the light from that artificial star will pass through most of the atmosphere and will be sensed and corrected for just like a normal star would be. But first of all, it doesn't quite sense everything because it's effectively not at infinity. It's at a finite distance from the telescope. So we're missing a little bit. And then more importantly, there's an important effect of tip tilt. The simple motion of the stars, random motion of the stars, is not sensed by this artificial laser because the light goes up and back down. So it sort of cancels out. So we still need a fainter star on top of the laser, in addition to the laser, I should say. And so when we have a bright star, it kills two birds with one stone, basically. We do everything with a single star, and it's nice and bright. In fact, most of the bright stars we looked at are a lot brighter than any star we can create, artificial star we can create at the moment. So it's more effective that way.
Okay, great.
I'm curious, looking at your chart, there's a huge leap between the years 2015 and 16. And I was wondering what happened in 2016 that can cause the increase in the number of detections?
Yeah, doesn't it look weird? To some degree, the same thing happened between 2013 and 2014. And it turns out that 2014 and 2016 were the years where we had a big dump of Kepler results. The first wave and sort of like the late phase wave of Kepler discoveries were announced in huge batches. As you can see, something like 1,000 planets each, maybe more than that for the second one. That's the discrete events you see there. So rather than announcing planets, 100 per month, they decided to wait a year and a half or two and then dump out 2,000 planets in one go, basically. In part because they wanted to double check and follow up and make sure, quality check everything and so on and so forth. And it was easier to do that in big batches rather than one at a time. But that's what happens in that chart. So in spirit, the data were acquired in a more smooth fashion, but they were just announced in these big jumps, big dumps.
Any final questions for Gaspard?
I'd like to thank you for coming. You did an outstanding job, and we really appreciate it.
Absolutely, it was a great pleasure.
I have a silly little question. I hate to. So Gaspard, as mentioned, we recorded this, and for the past meetings, we've been posting them up on our club's YouTube channel. Do you have any objection to us doing that with this one?
Absolutely not.
Fantastic. Well, I'll shoot you a link once we have it posted.
Great, fantastic.
Definitely do that.
Cool.
I didn't know we had a YouTube channel.
Yep.
You gotta come to these meetings more often, Richard.
I'm too busy doing astronomy.
He's too busy auditing.
It's not my fault anymore.
Yeah, I mean, Rick, all we have on there is the past recorded Zoom sessions that we've had over the past year.
Yep.
So there's probably what, 4 or 5 of them up there, Rob? Maybe half a dozen.
Yeah, we're missing the last couple though because we need to verify from the speakers. The fact that you asked them right now is a big help.
Saves a lot of time right there.
Yeah, cool. And we've got it recorded, so you can't deny it. Yeah, Rob. Maybe okay. Thanks for the heads up. I'll take a peek and maybe round up some of the other speakers till we get that completed.
Awesome. Because I'll apply when we get permission.
Cool. But yeah, Gaspard, again, thank you a bunch. That was a fantastic talk. And the theme has always been we try to make the most of the quarantine. And
I'm in favor.
Yeah.
Absolutely.
Maybe unmute for a round of applause here.
Yeah, let's do that.
Hey. All right.
Bravo.
Well, thank you. It was like I said, a great pleasure to meet you all. And I don't know if I get a chance to get to Delaware, but if I do, I'm definitely going to ping Richard and we'll get together at some point back in the days when we can actually travel again.
Yeah. I mean, if you're in the area, again, I'd be happy to take you up to the observatory and tour you around. And
we'd love to see that 50-inch telescope.
Yeah.
Nothing like a year from now, right?
Yeah.
All you have to do is fly into Philly.
Yeah.
Fair enough. Yeah, I can do that.
Refreshments are in your refrigerator.
Hey, I missed a cheese.
Walk right there.
Cool. Well, again, thanks for everybody participating. And again, we'll see everybody next month, if not at one of the astronomy workshop meetings between now and then. So have a great night, everybody.
Good night, everyone.
Good night, everyone.
Good to see everybody. Good to see you.